Bro, come here. Were you able to do it? Okay, thank you. Thank you so much. Thank you. Okay, I got it. Thank you. So, okay, I'm going to bring Samantha up. She's going to do a quick intro, and then we'll bring you back over. Sounds good. Thank you so much. Want to do the basics here. Yeah, come on in. We've got seats at the front. That wasn't me. Somebody's testing.
Can you guys come on back or come on up? Make sure that I'm just going to end it.
This is for the stream. This is for.
So stand close. Got it. So I just wanted to welcome everybody here tonight. Thank you for coming. We've got a great a duo of speakers tonight. Samira from Platform9, Ankush, our own JFrog senior developer advocate as well, Samira. So thank you guys for being here tonight. I wanted to take just 2 minutes, if I may. You may have seen that we had these postcards at the table when you logged in or when you checked in. It's about our annual user conference called Swamp Up. And I'm from the marketing team, so I'll just take 2 minutes before we get started. Swamp Up is a great way for you, if you're a JFrog customer, to get a handle on or better understanding of our products. We've got a great keynote lineup from Google, from AWS, from Uber. It's going to be a great event in May 16th to 18th up in Napa Valley. Please feel free to take one of these cards. And we've got a special discount tonight, located right there at the bottom, 15% off all tickets that you can choose on the site. And with that, all right, I'd like to go ahead and hand it to you.
Oh, thank you. Thank you. As she just said, my name is Tamara James. This is my first time at the JFrog office, and this is lovely. The green is real, I can see. Yeah, so my name is Tamara James. I'm a developer advocate for Platform9 systems. We're also based here in Sunnyvale as well. And so today I'm going to be talking about function composition in a serverless world, right? So throughout this talk, we're going to talk about what function composition actually is. We're going to go through a few examples, a few use cases in which function composition even matters. And by the end of it, hopefully you'll get more of a gist of the different styles of composition, and you'll have more of a gist of the purpose. First and foremost, it's going to be super key in this talk, is understanding what FAS is. So FAS is functions as a service, and functions as a service enables developers to be able to deploy independent specific parts of an application as functions on an as-needed basis. Let me not trip over this. On an as-needed basis, right? So what that means is you're able to actually deploy specific parts of your application instead of the entire application as a whole, right? So there are a lot of benefits to this. First and foremost, it's developer-friendly. And what I mean by that is it actually strips away the ops from the developer. So it strips the obligation of having to manage and maintain servers. And also, the billing model is pretty sweet, as you really don't have to, can you guys hear me? Okay. The billing model is really sweet. It's set up on a as-needed basis, as I said. So you only pay for the resources that you're consuming instead of, maybe the size of the server, the instances. Also, scaling services is simplified here with FAS as well. So what's function composition, right? So function composition refers to when one function communicates with another. And the purpose of this talk is to kind of iterate why the communication between FAS functions matters. And it actually plays a key part in a lot of different factors when it comes to deploying your functions in terms of latency, in terms of what you're actually using when it comes to resources, in terms of, there are a lot of different key factors. So how your functions communicate is really important. So throughout this talk, we're gonna actually be using an example. Our example project is an imaginary application. It is an animal photo filter. So imagine that you have this lovely collection of animal photos. You're weird like me. You have them stored on your device for no particular reason. Cute cat photos, cute elephant photos, monkey photos, all of the above. And what our application is going to do is actually analyze each of the photos via a third-party API, image recognition service, and categorize which ones are actually, which ones are dogs and which ones are cats. And of course, those are determined by the generated keywords from each filter. So there's two from each photo. So there are two functions, right? Two tasks. Function A is just simply going to send the photo to our third party for recognition. And then function B is going to actually filter and categorize them. So once we have the results, and we have, of course, we're going to have cats, we're going to have dogs in those, maybe an array of results. We're going to extract the cats and dogs and display them. So the first style of composition is Mayo Compilation. And there's something I actually wanted to get into before this. The different styles that I'm actually going to walk through, this one included, you'll be able to see the different styles of communication and why they actually matter and how they play out in terms of not only just syntax and composition, but in terms of, again, cost, efficiency, latency, and all of the above. So you'll be able to determine the differences as we go through the different composition styles. So the first one is manual compilation. It's probably the simplest, the easiest to understand, the easiest to actually execute, because what you're doing is you're merging all of your functions into one big function, right? So if you're a lazy coder like me, you're merging all of your tasks into one function on a source code level. So it's one big task from a FAS framework, the FAS framework's point of view. Is understanding all of the different tasks. Or was that me? What happened there? That's why I printed notes. But basically, the FAS framework understands this. Okay. So we have several different tasks. Let's look at the code. Okay. So we have whatever file. This could be a Swift file. I'm a Swift enthusiast, so this could be Swift file or any language. And we have our several tasks here. We have first function is sending the photo to our third-party service. And then the next function is just to filter and sort through those tags. And then we just create a new function to combine them. And that's basically it. So we've jumbled everything. All of the work is done within this one file. So the fast function understands all of these different tasks as one function. So it really understands it as the combined function. So there are a couple of pros and cons to this. Overall, pros, if you're doing this all at the source level, you really don't need a framework. All of your tasks are handled natively. So it's only one file, so it's fast at runtime. So no serialization overhead, so it's easier to debug. Everything is within, there's one source. And a couple cons to this. You know, for our example, it's a lot easier. We only have 2 functions, not many resources. But let's say you have something that's super complex. You definitely wouldn't execute something like this when when you have an application as complex as like a Netflix or something. That function, functions tend to get bigger and the load time tends to get a lot slower. Also, you can't scale, if all the tasks are in one file, you can't scale them independently, right? Because the fast function understands it as one task. So there's no way that you can scale the task independently. The next style is chaining. This is a little more common. You may have seen this anywhere with any of the supported the fast solutions. And yeah, so they form a chain and they basically call each other. So the functions are nested within each other and they're calling the next within via an HTTP call. So each separate task is a separate fast function. So it's similar to our compilation, but each task is separated in a function. And so and each function is also aware of the next function. So I have a sequence chart here just to kind of show you what's really happening behind the scenes. So with function A, which is sending our photo to the third-party API, we started that. And within the midst of that, right after we start doing that, we automatically send that HTTP call to the filter function. But while we're sending that call, we haven't ended. We don't end the function. That function doesn't end until the response comes back from the filter function. So there's a dependency there, and then there's a wait time there as well. Pros of this, it's easy to understand conceptually. You obviously don't need any external components for this. And this is supported by every fast platform. A couple cons, again, each function waits for the next function. So time is money and you're wasting time and you're wasting both time and money and memory. So that's a con. And then also you are responsible for handling failures, thinking about, retries, because thinking of that kind of structure, every function is making an HTTP call. So you're kind of depending upon the success of each HTTP call before another call is made. But service meshes like Istio can kind of solve this for you and kind of take that problem off your hands. Yeah, and they're tightly coupled functions. So again, if you have one function that depends upon the next function, whether or not that's executed, just think about the pains of updating one function. You have to update the next and the next, depending upon its predecessor. So it's a bit annoying. Coordinator functions, you probably heard this if you're familiar in the FAS community. Coordinator functions, basically, they act as directors for the rest of the functions. So there's one omniscient function, so knows all and does all. and it calls each function via a remote HTTP call, and it manages the entire execution in the flow. So it's similar to direct functions, except the other functions, every other function besides the coordinator, they're unaware of the other functions in the sequence. The coordinator is the only one that is aware of the sequence. So let's take a look at what's happening here. So the coordinator has to start. So the coordinator is an independent function. So the coordinator has to start, makes the HTTP call to function A, which is our photo analysis. It's making that call, then it has to wait for the A's response. Then once it gets a response from A, makes a call to B, waits for that response. So it has to wait for that entire life cycle before that function actually ends. So pros to this, you don't need to modify the primitive functions. The coordinator is responsible for everything. Super flexible, it gives you the power to control the flow and the sequence. And of course, no external components needed either here. Also, with power comes responsibility. You have to think about things like handling failures, thinking about fallbacks and retries. These are things that you have to think about every single time you write a coordinator function. So there's the overhead of just the extra function. And why is that such an overhead? For one, you have to pay for each function to be executed. That's one. For two, coordinator is a really long, just think about that life cycle, right? So the coordinator is waiting for each function. So we only have 2 functions. So not so long for those functions, right? But let's say we have 10 functions, right? And we have a coordinator function, 10 or 12. We're waiting for each of those to finish. And so that might take who knows how long. So the coordinator is just sitting there waiting, and that could be well beyond the supported maximum. A lot of fast platforms, they only support about 5 minutes as a maximum for functions. I think Vision supports 6 minutes, but once it goes over that, it's kind of like. The next is event-driven functions. This is another common one. Event-driven functions are functions emitting and reacting to events on message queues. So each function is tied to a request and a response queue using something called event triggers. And functions are joined together. If you can imagine mapping, it's all mapped out. So each function is tied to a request queue of another function and a response queue. So this is what it looks like. So we have a request going out to our function A. So that is our, again, in respect to our example. So that is our image being analyzed. Now, once our image is being analyzed, we're sending a response to say, hey, it's been analyzed. These are the results. And we're sending a request to our next function, which is for it to be filtered. And then there is a response given there. And all of this is done on a message queue. Kafka's pretty common. I believe we use Kafka and NATS as well for our message queues. Pros of this style, for one, it's pretty fault tolerant, meaning that once one function is executed, once it executes successfully, even if it dies right after, the rest of the function will still be able to survive and continue to execute. Also, the message queue handles networking errors. So all of those things you don't really have to worry about. So this is definitely a better approach than the direct or the coordinator approaches. And again, this is really commonly used and well understood, especially with NATS with the publish and subscribe method. Let me see. Cons. So this can be a bit confusing. Even though we have like a perfectly well, mapped flow, imagine if you have a bigger application, right? So you have a lot of other different functions that depend on each other. There's almost, it can get really messy, right? So there's almost no way of knowing. Again, they don't know who's evoking those events, right? Who's invoking those events? So they're kind of unaware. They just know they're being triggered. So you'd probably have to comb through and see, okay, is this function what's causing is this function the request is causing the request to this function? Is this function emitting a response in response to this? So again, and you can think about, if you think about that kind of web, it can be a little bit difficult to, update one function, right? So you don't want to mess everything else up if you don't know that it's tied, you don't know what it could be tied to, you don't know what it could do. So, you kind of lose your way in that. So again, it has to be manually orchestrated. And the last one is workflows. And workflows create a visual flow chart and a visual flow chart of function interactions, right? And so workflows is a new framework. It uses a new runtime framework to execute a flow chart of tasks. And each task is it's crazy to say function as a service function, but it's a FAS function. It's usually implemented with some, abstract language, YAML, some annoying, workflow specified or specific language like YAML. And so we specify each task and each function here. So this is specifying the sequence of the function logic. So we have our, image recognition task, which is directly connected to the filter photos task. And again, it specifies here that in order to run the filter photos, we need the recognized image. Pros of this is a centralized visualization of logic. And the functions themselves is very loosely coupled. They're unaware that they're being used in a workflow at all. The workflow engine takes care of things like latency, retry. So those are things that it takes away that what we call operational complexity. And the workflow engine actually learns from previous invocations to improve the performance. So there's like this warm functionality. Also, let's see. I kind of cover the fact that there's a workflow specific language to learn, usually YAML. I've seen some other companies use other languages as well, but YAML is probably the most common. It can be a pain to debug, mostly because the workflow's composition style is really new. So it depends on the maturity of the framework. So here are a few workflow frameworks that I know of, just a couple. AWS Step Functions, they use this. Azure Logic Apps, and Fission Workflows as well. We also have workflows. And so Fission Workflows is an open source serverless workflow framework. And it's integrated with Kubernetes and Fission. It's high performance. I mentioned that it was fault tolerance and easy to deploy on Kubernetes. And so I have a link here if you want to check out our Fission Workflows repo. I mentioned that we're open source. So if you want to be a contributor, holla at me. Yeah, we're going to be at KubeCon in Copenhagen. If any of you are going to be out there, we're going to be at OSCON and Velocity. So catch our talks at any of those three coming up soon. And just to recap, just in case you forgot, Mayo Compilation Basically, you're jamming all your functions into one. You're not separating any of your tasks or specifying them as separate tasks. You're just jamming all of it into one on the source code level. You have the chaining composition style, which is every function calls the next function or calls another function via an HTTP call. The coordinator composition style, which you have one function that acts as a director and controls the flow of the sequence. And event-driven, which is all of your functions they live on a message queue and they're triggered, they're binded by triggers, and they are tied to they're tied to requests and response of other functions, and that's how they are connected. And then we have workflows, which give you a visualization of logic between your functions. So that's our recap. And serverless is lit. That's all I have to say. This was too good of a gift, not for me not to add. I'm sorry. I couldn't miss it. Yeah, serverless is lit. And if you have time after the meetup or after my talk, come ask me why. Thank you. And join our Slack community. All right. Am I waiting to grab the mic? Or no? Any questions, by the way? Yeah.
So you showed that the YAML definition shows the workflow.
Yeah.
Couldn't at deploy time you could do AST analysis and based on the AST generate the YAML at deploy time?
Oh, generate the YAML? Yeah, you don't have to do it. You don't have to do it manually. But most people find some other way to generate YAML.
If you look at the abstract syntax tree at deploy time, you could generate the YAML.
Yeah. Yeah.
Can I get that?
Okay. Yeah. Go ahead. Yeah.
Doesn't that just put you back to the driven model?
Just a minute. So, which AST were you? Sorry, I'm Som. I contributed to a bit of the efficient workflow stuff.
Yes.
I'm an engineer on the efficient.
Yes.
So, which AST were you?
So in the first example, you had two functions and a function that calls.
Oh, you want to automatically determine.
Yeah, exactly.
We kind of thought about doing that, but it's not entirely clear that you can do that in all cases.
Right.
But
because essentially source code, you have AST and you render it to a language. So you're rendering an AST to JavaScript.
Simple for static cases or loops, if statements.
Yeah.
It can get arbitrary.
Yeah. Second question was, if you have functions you're calling one after the other, there's HTTP calls, wouldn't that add a lot of latency?
Yes.
Yeah, well, the HTTP call itself adds latency depending on you're in the same cluster, but the cost tends to be on serializing things. If you have a large object.
Yeah. So
you can use binary protocols.
So function as a service is interesting. The only thing that concerns me is we're going from modular things to monoliths again, because you have to reduce the latency between multiple calls to different machines potentially. You'd have to have monolithic functions to eliminate all these within data center calls from one function to the other.
I mean, people seem okay with microservices.
Sure,
but yes, there is a cost, but you can always use the cost tends not to be the HTTP but the serialization. So you can use
you're right. Microservices has the exact same cost.
Yeah. People seem to be okay with that trade-off.
Yeah.
Like it depends on the use case. Yeah. You kind of pointed out that there's a lot of similarity to event-driven, and the workflow system is an event-driven system.
Queue. My thing was essentially if I have like 3 endpoints and all of them get a user cookie or something, and I want to validate the user before my function executes. So in each of the 3 endpoint or function cases, I have to call validate user, which would do a HTTP call, validate the user, come back, and then I do my logic. So I had like a few milliseconds of round trip.
Let me get that. So input validation is actually a good example where manual compilation is probably the best. it's where you want different functions when you want them to scale differently, for example. If one is CPU expensive and the other is memory expensive, you don't want to combine them and make one enormous memory and CPU expensive.
Got it. Thanks.
Does YAML support the conditional workflow?
Yes, you can write an if statement. You can click on that GitHub link, and somewhere in there is an example. Find me after the Other questions?
Yes. All right.
Thanks.
All right, thanks. Hello. Hello. All right, thanks so much, guys. Feel free to grab another pizza or some beer, and we're going to bring Ankush back up here to do Where the Helm Are Your Binaries, talking about Kubernetes, Helm, Kubernetes registry. So, Ankush. Woo.
Yay. All right, perfect. Can you hear me? Okay, perfect. Nice talk. It's nice talk. Yeah. So it's nice perspective, like from source to runtime. My name is Ankush Chadha. I lead the solution development team at JFrog, which is focused on partnerships and open source projects. Like the two open source projects that we have worked on so far is Helm and Grapheus. We are one of the contributors. In fact, one of my team members, Shiva, one of the 10 contributors in Google Grapheus project is right there. Also, thanks, I forgot about that. So thanks to Samantha and Perlin to set this up. They're part of the marketing team. Okay, let's get started. So what I'll talk about today is like a different perspective of like source to Kubernetes journey. This one will be more visible in terms of the machinery. But this talk will focus on Helm. So we'll talk about the source of Kubernetes journey in general, but the talks is focused on Helm. So before I talk about the outline, I would love to ask a few questions. So who's using Kubernetes? Can someone raise hands? Okay. Who's like someone like written Kubernetes templates, like all the YAMLs, the painful YAMLs? Anyone? Okay. What about Helm charts? Go templates. Go templates. Okay, perfect. So you have to, the familiar face, you have to keep me honest. The first step, don't write charts if you're not familiar with Go templates. It becomes challenging after like 5th chart. YAML and Greek, it's not like a fun combination. So Go templates are pretty handy. So let me come back to the outline. So what's Helm? I'll talk about like what Helm is, why use Helm, and how to use Helm in a way which benefits you and also the community. To make the community successful, we just need to make sure that we are consistent. And I'll also very briefly talk about the scale related challenges with Helm. I actually gave a talk 2 months back at the Helm Summit. We are talking about the scale related issues with the Helm community is working right now. Detail of the talk is on YouTube, but I'll just briefly cover it today. And also a few takeaways. Okay, so what is Helm? So Helm is actually a very easy way to get started on Kubernetes. If you're new to Kubernetes, it actually hides all the complexities involved in deploying microservices on Kubernetes. It's very easy to start with. So say if you're new to Kubernetes, you want to install Jenkins or Artifactory, you just run the Helm install, like say Jenkins or Artifactory, and you have the microservice up and running. So the microservice needs database, it needs like say a messaging queue. So everything is installed like nicely and easily for you. The second is it's a package manager for Kubernetes. So it makes versioning and reusability like really easy. Without package management, it's like super complex to manage versions of the deployment and so on and so forth. And we don't need to reinvent the wheel. If someone has done the work in the past, like, okay, let's reuse the same and focus on the actual business problem. The third one is interesting. It also started doing the application lifecycle management. So for example, you can easily install, deploy, upgrade, roll back, and even delete like a bunch of microservices on Kubernetes. Now this is like a 20,000 feet architecture of Helm. It follows the client-server model. Helm CLI on the left, this client side. When I do like Helm init, what it does is it configures my local system like with Helm, and it points to an existing kube context. We can also change context on the fly. Then it also deploys Tiller, which is the server-side component on Kubernetes, right? And the Tiller has the templating engine. So any charts which are sent by the CLI, they're actually processed by Tiller, and eventually resources are installed on Kubernetes. So Tiller is the one which does hides the complexity from the client side. So this is like the high-level architecture, and Tiller is the one which is installed to do the lifecycle management as well. So it's going to install microservices together, upgrade them, can roll back, you can remove, and so on and so forth. Okay. So one way to approach this problem is like, okay, like from source to all the way to Kubernetes. Source, like as a developer, I pick up a language of my choice. I rely on package types like Maven, NPM, Conan. And even when I'm Dockerizing my application, I also need my OS packages as well, right? So from source to Docker, we are clear, right? Now what next? So I have a lot of microservices which are containerized. It's like really hard to run them without Kubernetes, without an like orchestration engine. So like in this case, if we do like these things, like say from, if you rely on objects such as like deployment, stateful sets, jobs, it becomes relatively easier to deploy something on Kubernetes. In fact, these are the mechanisms to deploy something on Kubernetes. Let's talk about them like briefly what they are. So deployment object is something like, say, for example, if you're using a stateless application, or maybe a stateful application, like highly available stateful application, but which is tied to NFS. So deployment is one of the objects to use. The second one is stateful sets. So if you have like highly available stateful applications, stateful sets are perfect to deploy those kind of microservices on Kubernetes, and so on and so forth. And corresponding to these objects, there are like controllers. So what happens is those controllers, they make sure that, hey, whatever spec I declared as part of my resources, like say, for example, for deployments, I declared that, hey, I need one container. I need these many CPUs, cores, memory, so on and so forth. This is my desired state. The job of controller is to make sure that, hey, my actual state is equal to desired state. Right? So these are the ways you can like use different ways to deploy microservices on Kubernetes. But then the question is like, hey, I mean, it looks simple on PowerPoint. So what are the challenges, right? So challenge is always in the execution. So I myself has written like a lot of YAMLs, like when Helm was, or when I was not using Helm, it becomes like quite complicated. And these are the challenges. So like, okay, I can write like a lot of YAMLs, but like typically if I need to install like a service on Kubernetes, like let's say it has 10 microservices. 5 of them, they are mine. 5 of them are like 30 microservices, like 5 of them are third-party microservices. So I need to write like a wrapper script to install like all of them, right? That's painful. Like, why do I need to maintain that? And the wrapper script is also required to like have some kind of a context that, hey, I need to install all of them together. I need to upgrade all of them together. I need to delete all of them together when I'm done with it, right? So it becomes pretty painful to manage these wrapper scripts. And we have written one of them as well when we are not using Helm. Also, the lack of dependency management, it becomes like really painful of like not relying on something which we have done in the past, which is not shareable and which we can't version, right? So it becomes like really challenging. The third one is the lack of conventions, which is like naming is hard, and if there are no conventions, it becomes this terrible experience. So like, for example, like input file name, if I like rely on someone else's files, maybe they have named the file differently. So it becomes like really hard to take care of all that stuff. Like naming is the last thing I want to worry about. The last one is can't add logic to templates, which becomes very challenging if I need to support like a variety of different use cases. It becomes like really challenging. So these are the challenges without Helm, right? What Helm, like, and all of these challenges goes away if we are using Helm. So there's no need to write, like, there's no good reason to write like a wrapper script. We can just use the Helm CLI to install, deploy, and do all those lifecycle things. Also, everything is tied together in the release. So, I mean, it comes with a context. So I can destroy a release, and release itself is like an object, and we can like access like few variables on the release to know like whether this is an upgrade, this is an install, so on and so forth. The third one is dependency management is done by charts, and a chart can rely on other subcharts as well. Like for example, say Artifactory is okay. That's the name of the chart, but it relies on Nginx. It relies on say databases. Those are all my subcharts which I define in my requirements file. So I just use something as is, which has been done by someone else who might be better doing that job. Like, okay, if I'm using database, the database company should ideally be writing their own charts. Then Helm also does, I mean, there are a lot of good conventions, like chart.yaml is something where you define, okay, what the chart is. Then values.yaml is the standard way to define what are my default values. This values.yaml itself like solves a lot of problems for me. Also, like if you do Helm create, it will create like a sample chart for you with following those naming conventions. For advanced cases, you can also play with starters. I myself have not played with starters yet, but if we need to follow like more conventions, like typically like this is common in like big organizations, so you can use starters. The last one is you can rely on Go templating, which we will cover shortly. So you can add logic that, hey, if there is no storage, what to do? If there is dynamic provisioning, what to do? If there's static provisioning, what to do? So you can add like a lot of conditions. So this is the chart structure. And I'll play with the chart as well. There'll be some hands-on. So this is like a typical, like a simple chart. So chart.yaml is where we specify what this chart is all about. You can list authors, GitHub URL, so on and so forth. Charts directly is where all the dependent charts are stored. Then there is requirements.yaml file where I list out my dependent charts. Then templates is pretty interesting folder. It's where like all my Kubernetes templates exist, except the two files. Notes.txt is a very handy file. If I deploy something complicated, the first question I ask is like, what do I do next, right? How do I access the service? All that content goes to notes.txt. So when I say deploy something on Kubernetes via Helm, the text of notes.txt is output. So I know what to do next, right? Which is pretty like very, very, very handy. Then there are the _helpers.tpl, the template file. It includes a list of templates which I can reuse in other templates, right? So it kind of promotes reusability. If there's a piece of code that I need to repeat, why do I need to repeat that stuff? So all those things can be part of the helper templates. And then eventually the values.yaml where I define the actual default values which are required to install my microservices. So that's one. The second is it's very easy to write charts if we know the objects which are involved. So values is one object which represents values.yaml file. Chart is also like one of the objects where I can refer to, like say maybe the chart name defined within the chart YAML file. Capabilities is very interesting. There's something which we haven't used yet, but with the nature of changes going in Kubernetes, like especially in a month and a half, we may soon use capabilities. So it's one way to it's one way to kind of specify the certification metrics. A small one, not the bigger ones, which like from the past. You can specify, hey, what version of Taylor I rely on, and what version of Kubernetes do I support. So you can rely on capabilities object and use it in your chart itself. Templates is pretty interesting one. So templates represent like the templates folder within the chart itself. So you can refer to the files like within the chart. Like a lot of people have done like cool things with the template object and hooks. So for example, like one of the limitations is like, hey, okay, if the config map didn't change, how do I refresh my deployment? So a lot of people, they have used the combination of template and hooks to kind of solve all these problems. Release is release, and files is like, okay, if you have like some other input file, you can still rely on the files object and access that stuff. Okay, now this is a reminder for me to go to the terminal. Now it's going to be interesting to do it in like using a right. Okay. Okay, perfect. Let me maximize. Okay, so is it looking good? I'm back. Okay. Okay. So Helm. Let's see what all repositories I am pointing to. So these are the repositories where I can pull the charts from. So this is the public one, which is and Helm community maintains it. So each time I publish my chart to this place, they actually run a promotion pipeline. They make sure it's following the best practice, and they actually run the install before they merge the pull request. Yep, and like in this case, I'm also using Artifactory as a Helm repo. So let's see. So Helm create sample chart. We'll create like a sample chart, like easy to get started. Okay, sample. Let me do clear again to be at the top. So this is something similar to what we talked about. Let's play with these YAMLs a bit. It's not a good thing to play. It's a pain, but we still have to go through. It's pain. Okay. So like this chart.yaml is simple. Like it specifies what my application version is. It also specifies what the version of chart is. So it's easily possible that, hey, my application version is constant, but I'm changing my deployment topology. So that's the time when we play with this version. Okay. All right. Let me use the cast. Here. Okay. All right. Let's see values. Yeah, these are values. I mean, you can comment stuff. You can. I mean, if it's simple, I would say like go with the flat model. But if it becomes complicated, like follow this structure. Okay. The main one is BI template deployment. Okay. So this is where the Go templating also comes in. So like all this stuff, the charts becomes readable, even though they are YAML, it becomes readable if you know a little bit about Go templating. So I'll just talk very briefly, which is good enough to like go through these YAML files of the charts. So these things, they have special meanings. If you like add like a dash, it becomes like totally different. So I've like myself like went through the pain to figure out like solve the white space related issues in the YAML. I'll talk about that shortly. So this is what my deployment looks like. My deployment template looks like. I specify the image which I want to run on Kubernetes, so on and so forth. One of the other interesting patterns which we have seen implemented with a lot of our customers, especially financial customers, is it makes it easy if you like over here, I'm only like configuring repository, but it becomes it's more practical to configure even the registry as well. So like say typically, like, okay, this is pointing on Docker Hub, but with financial companies, they just can't access something outside, right? They want to have like a local registry where they can pull stuff. So yeah, the standard one doesn't implement it like this, but we usually go that route. Okay. All right. So a simple chart can actually deploy a very complex topology. Like in this case, I have a pod running, which has like my main container. It can also have multiple init containers running, maybe a helper container as well, all all pointing to like a persistent volume for storage. And this can also rely on other dependent microservices with similar topology as well. So even a simple chart like this can actually do complicated things very easily. This is the beauty of Helm, that it kind of hides all that complexity from you. Okay, so I'll talk about the tips and the tricks. And this is like based on our experience, especially in the last 3 months, 4 months, talking to our customers from like banking to the software companies, and even partners in the Kubernetes domain. The first one is very handy, like Go templates. So this is a bit like, for example, this stuff is different than this. If there's a dash, what it means is all the white spaces before they are removed. And then if there's a dash like over here, it means all the white spaces on the right, including new line character, they are removed. If you don't know about this, there'll be a lot of like YAML errors that you have to deal with. The dot here, like which we see as part of my charts, it means a context. It means my current context, and I can change that context. So like these are things I never knew when I wrote my initial Helm chart. I never knew, and when I like wrote many Helm charts, like, okay, there has to be like a better way of doing this. And finally, like I went through the Go templating. So these are like good enough to start with. Then they're like if else and so on and so forth. They're complicated stuff which can be done, but this is good to start with. Then storage is pretty interesting. Storage is something which we learned in supporting our Helm charts with a variety of customers. Each of them, they handle storage differently. And we have seen like a lot of charts, like other like people, they're also following the same standard. So it just makes sense to have the same naming convention. It like makes it easy to reuse someone else's work. Like when say I'm relying on MongoDB and so on and so forth. So for example, if persistence is required, then use persistence.enable true in values.yaml. So this is the structure of my properties, which I should be defining in my values.yaml. Then dynamic provisioning. There will be a few clusters where the dynamic provisioning will be enabled. It's good to point to a default storage class. So let me step back a bit. So what is dynamic provisioning? Say if my microservice needs storage, then that storage will be provisioned automatically. Now, for example, if I'm pointing to a Helm chart, or if I'm trying to install a Helm chart, which has 3 microservices, they may need like say 3 storage. Like if I'm running on Google, I may need okay 3 Google persistent disks. So all of it will be provisioned automatically if I'm using dynamic provisioning. There will be clusters where there'll be a default storage class, and there will be clusters where like it makes sense to ask user, okay, what storage class you want the chart to use, right? So the persistence.storage class is one of the patterns which like most of the charts are using. Like if you plan to write your own charts, you should also like try to follow the same pattern, because it just makes the experience for the end user very easy. Then static provisioning. So it is still relevant, even though dynamic provisioning exists. There are pretty interesting use cases of static provisioning. We actually modified our charts a couple of weeks back to again start supporting static provisioning. They're good use cases, like maybe I just want to restrict the way I provision storage, right? That's one of the use cases of using static provisioning. The other one is I want to use existing PV. Like I don't want to create like terabytes of data in my cloud, bumping up my compute costs, memory costs, and so on and so forth. I just want to use existing PVs, right? I want to use existing data. So those are the still valid use cases, even though dynamic provisioning exists, but there is a use case to support static provisioning. In these cases, the chart should have like properties such as like persistence.existing claim. And again, like just try to be consistent with these naming conventions. It's going to be easy for the community to accept like these charts. So storage is one which varies based on the kind of customers. Network is another one, like support both like the load balancer and node port. Like if you want a service to be internally accessible, like node port is preferred, and so on and so forth. This one is interesting one. We actually implemented it 2 weeks back. So there are good reasons to modify a subchart, right? For example, MongoDB. I want to bootstrap my database. I want to create users, like a bunch of users and database name before my service actually goes up, right? So what we used to do in the past is we used to like modify the third-party templates directly, and then just call like one additional config map to like run a bunch of scripts to bootstrap my database. Like 2 weeks back, like when we don't like a lot of charts, is like, hey, this model is not scalable. I just don't want to maintain someone else's chart, right? So 2 weeks back, like one of my teammates, Jenny, she posted on the Helm users Slack, which is again like a very active and responsive community. We help each other out. So like any questions, like post to the Slack channel. So they mentioned that, hey, you can use hooks. So like in this example, we changed our implementation to something like this. So this is like my Kubernetes template. The kind of object is job. Under spec is where I declared my desired state. Then under annotations, I say that, hey, I want to run this template, execute this template post install of this component, which is MongoDB. So whenever the MongoDB container is up, I want this template to be executed, right? We don't need to modify like someone else's chart directly. So this is the model that can be used. Also, if we rely on hooks, and if we do like a Helm delete, it doesn't clean up these extra hook resources. So do enable the hook delete policies, otherwise you'll have like a lot of garbage floating around. So this was like a trick which we just came to know. It was there, we just had no idea. We came to know 2 weeks back and we implemented it right away. Okay, troubleshooting. Helm lint is very handy. The second one is like super handy. I'll actually try to run it right now. So Helm install dry run debug. What it does is it goes through the chart locally, sends it over to Tiller. Tiller has a rendering engine which parses all the charts, sends it back to the client side. So I actually know, okay, what the hell is Tiller planning to run on Kubernetes? Let me try to run one of them right now. Let's see. Yeah, typing with one hand is not, I really don't know what's going on. Okay, no, I don't want to modify this. Helm install. Okay, yeah. So if I run this, what happens is like whatever I have like locally is sent over to Tiller, and it gives me the modified version of my YAML files. So if like say deployment failed due to like maybe a missing white space, you'll know right away. This is something I literally use it like every other day. It becomes very helpful. Unfortunately, these are the only like two commonly used tools to troubleshoot these issues. I'm sure like they're more being developed, but these are the most commonly two tools used. Okay, so we talked about Helm. Now what, right? Okay, I'm good with the Helm. I created a lot of charts. One of the problems which we found about like 2 months back is when we start using a lot of charts, then the Helm CLI starts consuming a lot of memory. So when we created about like 100K charts and tried to use a Helm CLI on a container which is running only 512 MB, the Helm repo add itself fails. So we discussed, so this is like one of the talks which I did at the Helm Summit. We discussed like, okay, how are there different ways to solve the problem, which I'll talk about next. Yeah, number of charts. So it's very easy to reach this number, like when you're full on in microservice architecture, you have a lot of containerized microservices running. So any change in my app or the way I deploy things, or even my dependencies, if there is any change over here, like say if my OS package changed, or my Maven package changed, source code changed, the way I'm Dockerizing my application, it got changed, or my deployment topology changed. Maybe I added like say one more init container to maybe clean up, to do basic stuff like cleanup, right? Any change over here, it increments the version of the chart. So what we found is if it goes beyond certain scale, the memory consumption becomes like very high. This is how like we wrote a Helm chart to generate a lot of charts. And again, like this is public. I'm still working on it. I still didn't get time to write the README, but the code is public. So we are using the sidecar pattern. The main container is responsible to produce charts. The sidecar is responsible to get the chart and push all the way to Artifactory. That's how we are producing like 100K, more than 100K charts. And then once we have a repo with all these charts, we try to run a container with low memory, just do a simple Helm repo add, like boom, the Helm CLI crashes. We made the proposal. So the fundamental problem is the Helm repo only has like a single index file. The index file being large, it complicates and slows down like a lot of things. So like one of the problem was that the YAML parser, it was too big index file for the YAML parser to consume. So right now the Helm community is working on a more like a memory efficient version of the YAML parser to solve this problem. But the actual problem, the fundamental problem is it only has a single index file and nesting needs to be done. Now this change is not easy. An index is something which like really defines my repository. The way I pull anything, I push anything, search, all of these are impacted if I change my index. Then backward compatibility becomes like really hard. So this is like the eventual solution. But the short-term solution like which they are working on is they're looking for YAML parsers which are like very efficient in memory. But the indexing is the one which will eventually solve the problem. And again, like NPM also followed the same way. NPM, when it started, only a single file. I believe now it's nested. So it shared the same problem. And there are other problems, again, like it's part of the talk. I just don't want to go in detail. So a few takeaways. Go templating, it's your friend when you're dealing with charts. Use hooks. Just try to keep your maintenance cost in control. Use hooks whenever possible. Storage and network, these are the two key things which actually we just redid the whole thing like a couple of weeks back, especially by talking to a variety of customers and partners. Storage, you should like support variety as discussed, like storage enabled, not enabled, dynamic, even dynamic, like what's default, make it configurable, static, all that, and use the same property names. It's just going to be easy for everyone to use your charts. And network as well, like you need to support like variety of options. Helm lint and Helm install, dry run debug is again like your friends. So these are your best friends if you're like writing charts. These are the takeaways. There's a bonus takeaway. We plan to demo this initially, but we thought, okay, we'll make it public so that you can use these pipelines. So like over here, like in the sample, actually, let me go to the actual GitHub. It just makes it more easy for me to read. So rather than me giving the demo, like you can play with these files. So this is like a 5-step CI/CD process in Kubernetes using Artifactory, Jenkins, Helm. And one of the advantages of like Kubernetes is you can go from source all the way to Helm. And if you have a single source of truth for all the package types which are like required to run stuff on Kubernetes, you can even go backwards. So you can go from Helm to Docker. You can trace things from Helm to Docker, Docker to even the CI job which produced the Docker image, to the Maven package which is part of one of the Docker image layers, and even the CI job responsible to produce those Maven packages. So you can trace it back. And this example, it covers everything. So it's not like a demo. It's like there you can play with the scripts and so on. So it covers like, okay, how do you set up Kubernetes, how you install Artifactory on Kubernetes, how you install Jenkins on Kubernetes, how you do all the mounting socket. By the way, the community is working to get rid of this as well. Mounting socket, especially to build Docker images, is like a security issue. And the community is working to eliminate this requirement. I'm eagerly waiting for it. Also, the 5-step CI/CD process, we have made the Jenkins pipeline scripts public. So like in the first step, you build the WAR file, there's a promotion process, you run the test, promote artifacts to production repos. Then similarly, you create your golden layer, which has your base image and the application server. Like in this case, we are pulling all of it from Artifactory as it's a Kubernetes registry. Then you Dockerize your application. Then you create the Helm chart. Then you use the same Helm chart and deploy it on a Kubernetes cluster. So all of these scripts are public. We would actually encourage you to contribute. Like feel free to file, and contribution is anyway, like you can feel free to file issues, submit PRs, and make it more robust. And yeah, that's about it. If there are questions, I'm happy to answer.
Just for the purpose of playing around, does this work on Kubernetes on Mac and Kubernetes on Windows?
Yeah, you planning to run Windows containers?
No, planning on running Linux containers, but
yeah,
my laptop is my work environment. So
yeah, no, yeah, all of it works. So like because even on Minikube it will work. Okay. Yeah. So the reason I was asking about the Windows one is like on a Mac, we need to make like a switch for it to run Windows containers. Linux containers are perfectly fine. So you can even run all this stuff on Minikube.
Yeah, no, just either environment that we may have at that time.
Yep.
So, okay, cool.
Okay. Any other questions?
What language is written in?
Go. Yeah.
So on the OS, what kind of dependencies it has to kind of just get started?
With Helm?
With Helm.
Nothing. Are you using Mac or do you install Helm? Okay. That's it. Yeah. What all dependencies? I think that's about it. So the best way to get started is you can either use Minikube. I think a lot of cloud providers they offer. Again, don't quote me. I think they offer a cluster, Kubernetes cluster, free for 30 days. So there are different ways to get started, like install Kubernetes, and Helm is easy to install.
Do you use CLI to deploy?
CLI, yeah, CLI. So Helm CLI to like install or upgrade, rollback if something fails, and even delete. Go. Yeah. So CLI, yeah. Helm CLI is so Days was one of the companies which wrote Helm. Now they're part of Microsoft. Yeah, and we contribute to Helm. We are not the ones who wrote Helm. We contribute, like say, one of the team members, they actually submitted a PR pull request to support basic auth in Helm CLI. And we are working with the Helm, like 2 weeks back, I was on a call with them to define like how the Helm push should look like. Yeah, I mean, there's still a lot, at least for us to contribute in that community. But it was the original work of Dias, which is not part of Microsoft. Okay, any questions? Cool.
Does this work with OpenShift?
Good question. Yeah, very good question. It does work. So, so I played with OpenShift myself. Actually, when I had to write the templates myself without using Helm, that was the time when I was working on OpenShift. How to get it up and running on OpenShift is you need to deploy the tiller pod manually. So the tiller is the one which handles connections with the CLI, the Helm CLI. So you can get it up and running, right? But it is not officially supported by them. So in fact, there's a blog post from Red Hat as well. This is how you can get up and running with Helm on OpenShift. Again, like you just run the deployment, like OC, like create or reply, like run that YAML file. It will install a tiller pod on OpenShift. Once tiller is up and running, you just need the Helm CLI to point to it. And actually the Helm CLI will rely on the existing kube context, which points to OpenShift. So you don't have to do anything else. But you can play with it, but I don't think Red Hat supports it officially. Even though the blog post is from Red Hat.
Because we directly don't use Kubernetes, we deal with OpenShift.
Yeah.
Wrapper on top of Kubernetes.
I think the Red Hat, actually, that's a good question to ask on the OpenShift Slack. Even I asked them multiple times. I never get the actual answer. But I believe they are, I'm not familiar with the service broker. They're going in a slightly different direction. Though this Helm is something which works, but like in terms of support, I'm not sure. Yeah, it's right up. It's gonna work. It just depends. Like, what do you mean? Like, what's the definition of work? It's gonna work if you are playing with it, but it won't work like if it's on production because there's no support. Okay. And but that's a good question. Actually, we also have the same question. We spoke with that team multiple times on this.
So you mentioned Jenkins as one of the CI, right? So other than Jenkins, like I would use Team City.
Yeah, I'm sure there'll be a Team City Helm chart. Actually, let's find. So QApps. .QApps. So this is the way where like all the charts are stored. I believe this is from Vietnamese Team City. Let's see. There's no chart. This is very surprising. Maybe on the regular, the official, they might have it. Let's see. I'm pretty surprised there is no Helm chart for Team City. Maybe the official, actually no, it also pulls from the official one. You have to go back and check. Usually, at least from the CI perspective, you see like pretty much everyone out there with their own version of Helm chart. I'm pretty surprised Team City is not there. But it should be easy to write one chart. Any questions? All right, cool. Thank you. Done?